Hi, and welcome to my presentation. My name is Darya Melnyk, and I'm a PhD student at the DISCO group, that is a distributed computing group at the ETH Zurich. I suppose many of you joined this presentation because you're interested in blockchain protocols, Byzantine Agreement, or distributed communication protocols in general. In that case, I think that you will find this presentation interesting because I will show that the DAGS structure for blockchain systems is better than the chain structures, and how ideas from the shared memory model can be used in order to simplify blockchain analysis. In order to publish a block on the blockchain, a miner would have to first solve a crypto puzzle and could then append its block to the longest chain. And then only the blocks inside the longest chain will be considered as valid. So the crypto puzzle makes sure that not too many blocks are appended concurrently, and therefore not too many blocks would have to be discarded in the end. So on the other hand, we have the DAGS structure. The DAGS structure can be thought of as an inclusive blockchain. Here, new blocks are always appended to all the children that a miner sees inside the DAG when it appends a new block. In the end, also the longest chain would decide on how to order these blocks of the DAG, but at least all blocks would be this way published sooner or later. There are several measures that can be used in order to compare the chain and the DAG structures. One is, for example, the throughput. That is, how many transactions can be made within a given time frame. Here it is obvious that the DAG structure has an advantage if the rate at which the blocks are appended is high. If the rate, on the other hand, is low, then only one block would be appended at a time, and therefore both structures would look alike. In our work, we compare these two structures with respect to their resilience, that is, how many malicious miners these two structures can tolerate. For the chain, we would need to make sure that not too many malicious blocks were appended to the longest chain. For the DAGs, the situation is not as clear. The miners could collaborate and append their blocks only to the longest chain, thus altering the whole DAGS structure. So it is therefore not obvious how many malicious parties such a structure can tolerate. In the paper that I'm presenting now, we introduce a novel communication model in order to simplify the analysis of the chain and the DAG protocols, which would allow us to have a simpler discussion of the resilience of both models. The standard model in which blockchain protocols are considered is the message passing model. In this model, we assume that the nodes are communicating over a peer-to-peer network and that over the channels of this network, message delays can occur. In addition to this, the nodes have to maintain a local view of the chain, and in order to append a block to the chain, a node would have to send this block over the channels of the network to its neighbors and wait until the neighbors have acknowledged that they have appended this block to their local view of the chain until this node can consider this block written to the memory. So in order to analyze blockchain in this model, one does not only have to consider this network, but also the consistency of the local views so that the chain is consistent in all nodes. This kind of analysis has been performed by Rein in 2019. In our work, we wanted to simplify this communication model by simply considering the shared memory model instead of the message passing model. Indeed, the shared memory model can be simulated by the message passing model, and therefore the results from the shared memory model also hold for the message passing model. In the shared memory model, the nodes are only communicating with the memory, and each node thereby has a register in this memory to which it can write its own values. In addition, the nodes can read other registers to retrieve the view of the whole memory. In order to make the shared memory model applicable to the blockchain and the DAG protocols, we had to extend it by two properties. One is that the memory in the registers should be unbounded so that the nodes can add more and more values to the chain. And the other extension is that the nodes should be able to snapshot the whole memory so that they can receive the whole view of the chain. We also call this model the Append memory model. In order to see how a chain can be maintained in such a shared memory model, we can simply let a node add blocks to its own memory. In order to make sure that the nodes can maintain a chain, the node can also label these blocks with IDs and then refer to previous blocks by using their IDs, so by only mentioning them in their own register with the ID. Another view of this model can be the following, that we have a shared memory where we maintain a DAG, and that the nodes simply have a read and an append access to this memory. If a node wants to read the memory, it gets the whole view of the DAG as a response. And then if a node would want to append the memory, it would have specified to which state of the memory the node wants to append a new block. So in this case, a correct node would simply append to the two children of the DAG the new value v. If another node would want to append its value, this node could have read the memory at the same time, and then it would append its block to the same state on the memory. But if the node arrived later and saw the newer memory, then it could or would actually append its value to the latest state of the memory. Besides correct nodes in the system, we also have Byzantine parties. A Byzantine party does not have to follow the protocol, and it also has knowledge of the DAG structure. So it can actually just go and append its values to some older states of the memory. The only thing that it cannot do is to violate the DAG structure. So if it would violate the DAG structure, it would reveal itself to the other nodes, and therefore the other nodes would just disregard this node's values because they would know that this node is Byzantine. And in this append memory model, our goal is later to solve Byzantine Agreement. And as in Byzantine Agreement, we will consider two different communication models. One is the synchronous communication model, and the other is the asynchronous. In fact, we will call our nodes synchronous or asynchronous because it is a shared memory model. And we call a node synchronous if the time between any two operations of this node is bounded by some constant. So the time between submitting a read and receiving the view of the memory is, for example, bounded by some known constant delta, and the time between appending a value and this value being visible to other nodes is also bounded by this constant delta. In the asynchronous model with asynchronous nodes, this cannot be assumed. Here, a node that reads a value can only be assumed to get this view of the memory eventually, but not after a certain bounded period of time. So this actually nicely corresponds to the synchronous and asynchronous model and the message passing model. So in this model, we would like to solve Byzantine Agreement. Therefore, instead of assuming that the blocks contain transactions, we simply assume that each block contains one binary value, which is either -1 or +1. We also consider correct parties, which are minors that always follow the protocol. And we assume that there is a Byzantine adversary that knows how the memory looks like, that controls all Byzantine nodes in the system, so that it can always append several blocks to the longest chain, and that this Byzantine party can also control the scheduling. In order to solve Byzantine Agreement, we need to satisfy the three properties of termination, agreement, and validity. Termination means that the nodes have to decide after a finite time on a value. Agreement means that they have to decide on the same value. And validity is a condition that makes this whole decision non-trivial, meaning that if the correct nodes had the same input value already, they also have to decide on this value as their output. So now we can discuss which properties Byzantine Agreement satisfies in the append memory model. Here we will differentiate between synchronous and asynchronous nodes. In fact, it can be shown that the append memory model satisfies the same bounds as the message passing model, namely that Byzantine Agreement with synchronous nodes would require at least t+1 rounds, while asynchronous Byzantine Agreement is as well impossible in this model. This is not surprising because the append memory model, just as a shared memory model, can be simulated using message passing. In order to do so, we can consider the two commands. The first one is the append command. So if a node would want to append a value to the DAG in the message passing model, it would simply send this command to all nodes in the network. It would wait until almost all but the Byzantine nodes have responded to its command, and will then consider this value as written to the network. Now, if another node would like to read the current state of the memory, this node would send a read command to all other nodes in the network. It will then receive views of the snapshots of the single nodes as a response. And from these views, it would need to reconstruct the whole memory view, the current view of the memory. So here you see the three snapshots of the memories of the nodes. And you can see that the first three nodes are the same for all views, while the views differ in the last value. So two of the nodes have actually included the newest value v that was just appended, while the Byzantine party tries to append some other value to the memory. In order for a block to be accepted, this block needs to appear in at least half of the views. Otherwise, this block is just discarded. So in this case, the value v will actually be accepted into the memory, while the Byzantine value will be discarded. And therefore, the node that was reading the memory would simply adapt the memory view M1 or M2. And this is how the append memory model can be simulated in the message passing model. Finally, I would like to come to the resilience analysis of the blockchain and the BlockDAG structures. Before diving into the analysis, I want to discuss the memory access. At the beginning, I said that the miners have to solve a crypto puzzle in order to append their blocks to the chain. This way, the blocks that are appended to the chain are appended to it with respect to a Poisson process with rate lambda. If we would remove this restriction on the memory access, the nodes would actually just behave as asynchronous nodes. Therefore, in order to solve Byzantine Agreement, we do not only need to make sure that the nodes in the system are synchronous, but also that the memory access is restricted. In order to discuss the resilience of the chain, we need to take a look at the longest chain in the system. If the blocks of this longest chain were appended by only Byzantine parties, then even if termination and agreement would be satisfied, the validity property would be violated. Therefore, we need to make sure that there are more correct appends to the main chain than the Byzantine ones. So the first situation is actually possible if the number of correct and Byzantine nodes in the system is the same. Then the correct and the Byzantine nodes would append to the system at the same rate, and the Byzantine nodes can make sure that they form a chain with their own values. In order to prevent this, we need to restrict the number of Byzantine nodes. So if the number of Byzantine nodes is only 1/3 at most, then at most every third append to the memory will be from a Byzantine node. The Byzantine node can still make sure that it appends concurrently to correct nodes. Therefore, the next correct node that would be appending its value on average would, in the worst case, append its value to a Byzantine value. In our paper, we could show that the resilience of the chain actually is indirectly proportional to the rate at which the blocks are appended. So the higher the rate at which the blocks are appended, the lower the resilience of the chain. If we, on the other hand, consider the resilience of the DAG, then the Byzantine strategy could also be to append to the main chain, as the main chain will be part of the decision. But in this case, we can also expect that there will be from time to time one correct node that makes sure to address a correct and a Byzantine node, thus combining the DAG again. Therefore, the Byzantine nodes need another strategy in order to be able to get more Byzantine values into the chain. And since we are solving Byzantine agreement, this is actually possible. This is because at some point the nodes have to terminate. So after a certain number of appended values, the nodes have to decide. Therefore, the Byzantine party can make sure that just before the decision, it adds a longer chain of Byzantine values to the DAG. This way, it changes the main chain and makes sure that the correct nodes, or some of the correct nodes, are not part of the main chain anymore, and therefore will not be considered for decision, while the Byzantine nodes will be considered for decision instead. The number of Byzantine nodes which can be added in this way highly depends on the rate lambda and the difference between the correct and Byzantine nodes, which is n minus t. If we increase the number of nodes that are appended to the chain, we can, however, still achieve the optimal resilience of 1/2 in this system. So the analysis of the DAG structure actually looks quite simple here, and this is because we managed to abstract away all the communication that is happening in the background by using the append memory model. So now I would like to show you how the number of blocks that need to be appended to the memory before decision depends on the difference of the correct and the Byzantine nodes. So if the difference between the correct and Byzantine nodes is just a constant, then the nodes have to append at least lambda n log n blocks to the memory. If, however, the difference is larger, so we have something like at most n-third Byzantine nodes in the system, then already lambda log n appends to the memory are sufficient to solve Byzantine agreement. So in summary, the results of the paper that I've just presented include a novel shared memory model for blockchain protocols, the so-called append memory model. In particular, the append memory model allows to abstract away all the communication overhead of peer-to-peer networks, and it is therefore easier to analyze blockchain and DAG protocols in this model. Using this model, we could show that the BlockDAG can tolerate up to 1/2 of Byzantine nodes, while the resilience of the blockchain depended on the rate lambda. In the future, I think it would be interesting to consider other blockchain protocols in the append memory model, or maybe even Byzantine agreement protocols. If you're interested in discussing this further, please join the virtual session number 3 on July 15. That being said, I would like to thank you for watching my presentation, and I'm looking forward to seeing you at the virtual talks.